Welcome to the second lecture of joint probability distributions. As you recall, in the first lecture, we did discrete bivariate random variable. So here I have written all the definitions related to discrete bivariate random variable that we discussed in the previous lecture. So let's see these definitions first, because these will help in understanding the definitions related to continuous bivariate random variable. Okay? So let's see what's a bivariate discrete random variable. If x and y are two discrete random variables, then this pair x comma y is called a discrete bivariate random variable. Okay, first definition. Then what is a joint PMF? A function fxy is a joint PMF of xy if it satisfies three properties. What are these three properties? fxy should be non-negative. Number two, fxy should give probability for each value of x and y. And third, sum of fxy over all xy is 1. So with these three properties, fxy is joint PMF of xy. Okay. Next definition that we did is marginal PMF. What is marginal PMF of x? It is summation of fxy over all y. If we sum the values of fxy over all y values, then it's marginal PMF of x. Similarly, marginal PMF of y is summation over x fxy. Third definition, independent random variables. As you recall, when we say xy are independent random variables, if the joint PMF is equal to the product of marginal PMFs for all xy, then x and y are independent random variables. Okay. Fourth definition, expectation. Expectation of any function of xy is what? Double summation hxy fxy. In particular, if you replace hxy by x, it is mean of x. Similarly, mean of y is ey. Next definition is covariance xy. That you recall is exy minus ex into ey. And the next definition is cumulative distribution function or CDF. What is it? Sum of probabilities up to the given values of xy. So double summation x less than equal to x, y less than equal to y, fxy. This gives you CDF. So after these definitions, let's see what is a continuous bivariate random variable. If x and y are two continuous random variables, then x comma y is defined as bivariate continuous random variable. Okay? The definition is similar to this one. Now, what is joint PDF or joint probability density function? See the difference here. Here we are calling it probability mass function. Here probability density function. So joint PDF of xy is a function of xy which satisfies three properties. One, fxy is greater than equal to 0. Two, it gives probability for any region R in the xy plane. Means probability of all xy belonging to the region R in the xy plane. Means the fxy gives probability for any subset of the xy plane. Third, double integral over all values of xy is 1. Now you can make comparisons. First condition is similar. Second, it gives probability for each value of xy. But here, for a particular value of xy, probability would be 0. Here you need to consider a continuous region for xy. Okay? You know x and y are in plane. So R could be something like this. So over this region, if you want probability, then what to do? Just double integrate your joint density function over that region. And third one is you understand that it is the integration over whole xy plane, over the full ranges of xy. If it is, it should be 1. So with these three properties, fxy is joint PDF of xy, or you can simply call it joint density of xy. Okay. Now let's see the next definition, that is marginal PDF of x and y. So marginal PDF of x in particular is integration of fxy over the full range of y. If you integrate the joint density over the full range of y, we get marginal density of x. Similarly, marginal density of y is integrate fxy over the full range of x. So what has happened here? You have summation, here it's integration. Summation sign has gone to integration. Next, independent random variables, definition is similar here also. If joint PDF, or you can say joint density, is equal to the product of marginal PDFs, or you can say marginal densities for all xy, then xy are independent. So definition is similar. Now look at the fourth definition, expectation. You can guess the definition of expectation yourself. Here, EHXY is double summation over xy. Then HXY, FXY. What should happen there? Expectation of HXY in the continuous case should be double integral minus infinity to infinity, minus infinity to infinity, HXY, FXY, dx dy. Again, you can see that this double summation has gone to double integral. Okay. Next, covariance definition is same in continuous case also. But you should understand that EXY now is to be calculated using double integral, not using double summation. Here you will calculate EXY using double integral. How? EXY means double integral XY into fxy dx dy. Similarly, what should be CDF means capital Fxy in the continuous case. Here it is sum of probabilities up to x. There it is double integral minus infinity to x minus infinity to y fxy dx dy. Okay. One more thing that you can interpret here, because now you have a continuous region and fxy is a continuous function. So what is the meaning of this result? What is the meaning of this result? First, you should recall that fxy graphically is a surface in 3D space. Okay. So this is volume under that surface. Just like you did in single variable case, single continuous variable case, what you did there? Area under the probability curve is 1. Here, volume under the surface fxy is 1. Right? So total volume under the probability surface is 1. Under means above xy plane. and below the surface fxy, the total volume is 1. So this kind of geometrical interpretation you can understand. Alright, so we are done with all the definitions. Now we can do some problems. So let's see first example. The example reads, suppose X denotes a person's blood calcium level. Blood calcium level. And Y denotes blood cholesterol level. Joint PDF of XY is given by fxy equal to K for X varying in the range 8.5 to 10.5 and Y varying in the range 120 to 240. 0 elsewhere. Okay. So these are two continuous random variables, blood calcium level and blood cholesterol level, and this is their joint density. Now the first question is, what is the value of K? If it is joint density, then how to calculate K? Look here, there is a condition in joint density. Double integral over the full range of xy should be 1. So you can use this condition, and according to that condition, what should you write? X varies from 8.5 to 10.5 in your problem, and Y varies from 120 to 240. In these ranges, fxy is K, elsewhere it is 0. So you just do your calculations using these ranges. Put this equal to 1. Because if it is joint PDF, double integral over full ranges of xy should be 1. So after solving this double integral, please do yourself. What do you get? K equal to K equal to 1 over 240. This is the value of K if you solve this double integral. Then next part, find marginal densities of X and Y. You can see the definitions here for marginal densities. If you need marginal density of X, integrate over Y. Integrate over the full range of Y. So what's marginal density of X in this problem? Range of Y is 120 to 240. And integrate your fxy. What is fxy? Now you know the value of K. So your fxy is 1 over 240. So integrate over Y. What do you get? It's simple integration. You get 1 over 2. Similarly, you can calculate marginal density of Y. How? This time you will integrate your joint density over the full range of X. It is 8.5 to 10.5. Again the joint density is K, so value of K is 1 over 240. This is the range of X, so you will write dx here. If We integrate it, what do we get? We get 1 over 2, 1 over, what do we get? 1 over 120. So these are marginal densities of x and y in this example. Okay. Now you have joint density, which is 1 over 240 in this range, and these are marginal densities. Looking at these, what can you say about the independence of x and y? Are x, y independent here? Check it. In your problem, fxy is k and k is 1 over 240. Is it equal to product of marginal densities for all xy? Yes. You can see here 1 by 2 into 1 over 120 is 1 over 240. So in this problem, xy are independent. Means blood calcium level has nothing to do with the blood cholesterol level. Okay. Now let's see the next part of this problem. Before I ask you next part, do you understand the region of integration here? See where xy are varying. X goes from 8.5 to 10.5. Let's say here x is 8.5, here x is 10.5. Y is varying from 120 to 240. So what is the common region to all these 4 straight lines? This region. This is your region of integration. Okay. Now I ask you third part in this problem. What is the probability that the person's blood cholesterol level lies between 150 to 240? Cholesterol level between 150 to 240. You know why it denotes the cholesterol level? And it goes from 150 to 240. Let's say here y is 150. So what do you need in this problem? How to calculate this probability? You will integrate your joint density over this region because there is no restriction on x. The restriction is only on y. So to calculate this probability, just double integrate your joint density, that is k, and k is 1 over 240. What are the ranges of xy for this? X goes from 8.5 to 10.5 and y goes from 150 to 240. So simplify this double integral. What do you get? You should get 5 over 12. Please check it. Okay. One more calculation you can do, that is of covariance xy in this problem. Covariance xy means exy minus ex into ey. So how to calculate exy? double integral xy into fxy over the ranges of x and y. Likewise, you can calculate ex and ey. I'm just writing directly the values of those integrals. Please verify yourself. The values are exy value is 1710 minus 9.5 is the value of ex and 180 is the value of ey. Finally, you get 0. You get covariance of xy 0. X and y are independent, covariance is 0. There is some connection. We will learn it soon, okay? So, this example is over. Now let's move to the next example. Example 2. Write the statement. The joint PDF of xy x comma y is fxy equal to c over x for xy in this range and 0 elsewhere. Okay. First question is, what is the value of C? So because we are saying it is joint density, so just as we did in the previous part, we will double integrate joint density over the given ranges of xy and put that equal to 1 to get C. But before that, you should know your region of integration. What is the region of integration in this problem? If you see here, it looks like y goes from 27 to 33, x also goes from 27 to 33. But there is something more. Let's see the region of integration. Y goes from 27 to 33. Let's say y27 here, y33. X goes from 27 to 33. Let's say x is 27 here and x33 somewhere here. So what do you think? This is rectangular region? No. See this line. This line is y equal to x. There is one more condition. Okay, xy vary in the range 27 to 33, but y should be less than equal to x according to the given condition. So in which region y is less than x? Less than equal to x? In this whole region. So this triangular region is in fact the given region of integration. Okay. Alright, so how to find the value of C? First part. You need to double integrate the joint density. Double integrate joint density means C over x over the ranges of xy. Now the thing is that what are the limits of xy in this region? I believe you are familiar with double integrals. So for a triangular region, what to do to find the limits? Either you choose a ray parallel to x-axis or parallel to y-axis and write your limits. So let's choose a ray parallel to y-axis. See where it enters the triangular region and where it leaves the triangular region. It enters here. So what is y here? It is given it is also written here, y equal to 27, and here y is clearly x. Okay. So y limits are from 27 to x. X limits leftmost point of the region and rightmost. Leftmost point x is 27 and rightmost x is 33. On all these points x is 33. So it should be dx dy. dy dx or dx dy? dy dx, yes. Should be dy dx, because these are limits of y first. Put this equal to 1 and simplify. Simplify this double integral. Please do it yourself. When you simplify, you get value of c equal to 1 over 6 minus 27 ln 33 over 27. Also check that if I choose a horizontal ray in this region, means if I change the order of integration, do you face any problem? You can check it the other way around, the calculation would be lengthy. Okay, you see it yourself. So this is the value of c that was required. We have found it. Second part, marginal density of x. Marginal density of x in this problem. What to do? Integrate your joint density over y or x. You are finding marginal density of x over y. So what is y range? You can see if you draw a ray parallel to y-axis in your region, the limits of y are from 27 to x. So just simplify the single integral. What do you get? You get c times 1 minus 27 over x. Okay. Similarly, you can calculate marginal density of y. This time you will integrate your joint density over x. What are limits of x in this region? Now choose a ray parallel to x-axis. See where it enters, where it leaves. It enters at x equal to y. Here you can check x is y. And where it leaves on this line where x is 33. Enters at x equal to y, leaves at x equal to 33. So limits of x are from y to 33. So integrate it and see what do you get. You get c times ln 33 over y. Okay. So we are done with marginal densities. There is one more part in this problem. Let's do that also. Third part. Find the probability in the region where x is less than equal to 32, y is less than equal to 30. X is less than equal to 32 and y less than equal to 30. First, you should identify your region. Once you identify your region, you will come to know the limits of x and y. So see here, in this triangular region, where are these limits, or where are these ranges? X less than equal to 32. Let's say x is 32 here, somewhere here. So this line is x is equal to 32. Next, y is less than equal to 30. Y less than equal to 30 means somewhere here. This line is y equal to 30. Okay. Y less than equal to 30 means this side. X less than equal to 32 means this side. So this is the region where you will need to integrate your joint density. This is the region where you will integrate your joint density to calculate this probability. So joint density is C over x. But before that, you should know the limits of xy. So how to decide limits of xy in this region? Choose a ray parallel to x-axis or parallel to y-axis. If you have done double integrals, you know a ray parallel to x-axis would be helpful. You can deal with the whole region. This way, it enters at x equal to y, leaves at x equal to 32. Enters at x equal to y, leaves at x equal to 32. Limits of y are from bottommost point y is 27 and uppermost points in this region y is 30. So these are your limits of xy if you choose a horizontal ray through your region. Alright, so limits order is dx dy. Okay, once limits are known, it's a simple double integral. Simplify it. And once you simplify, you should get c times 3 ln 32 plus 3 minus 30 ln 30 plus 27 ln 27. This is your answer for this probability. I'm writing all answers in C. So C has already been calculated earlier. So you know your answer precisely. Okay. Okay. So we are done with this example. Let's see next results. There is a theorem related to the independence of continuous random variables or discrete random variables x and y. What is it? If x, y are independent random variables, then EXY is equal to EX into EY. Let's prove it. It's an important result. Let's prove it. So for proof, notice that x, y are independent random variables. What does it mean? Joint density is equal to product of marginal densities. Next, what do you want to prove? EXY is equal to EX into EY. So let's start with EXY. By definition, what is EXY? Double integral xy fxy dx dy over full ranges of xy. Okay, by definition, this is EXY. Now, because fxy is product of these two, so you can replace fxy by fxx into fyy. Okay, after that you can rearrange it to write the inner integral is with respect to x, so y is constant for it. Likewise fyy is constant for it, so you can write it outside, and inner integral is minus infinity to infinity x fxx dx. See, what is it by definition? It is Ex. This integral is Ex. So what is left finally? Ex into minus infinity to infinity y fyy. This is what again? Ey. So finally you have Ex into Ey. This is what we were looking for. So if xy are independent random variables, Exy is equal to Ex into Ey. It has further implication. What? Covariance xy in this case would be 0. Why? Because covariance xy is the difference of these two. So if these are equal, then covariance xy is 0. Now the question is whether converse of this result is also true. The answer is no. If covariance of two random variables is 0, then you cannot say xy are independent random variables. So for that you need to know one counter example if you want to disprove this. Let's see that example. Before that, if you want to prove this for discrete random variable, I have not written anything here, continuous or discrete, but I have given the proof for continuous. You can give the same proof for discrete also. What will be the change in the proof? The double integral would be replaced by double summation. Steps are same. Okay. So now we are looking for an example where covariance is 0 but xy are not independent. See this one. Xy are two discrete random variables with this joint PMF. X is taking the values 1, 4. Y is taking the values minus 2, minus 1, 1 and 2. Probabilities are 0, 1 by 4, 1 by 4, 0, 1 by 4, 0, 0, 1 by 4. Let's write marginal densities also. Here fxx values are 1 by 2, then 1 by 2, this side fyy values are 1 by 4, 1 by 4, total is 1 on either side. So this is the joint PMF of x and y. For this joint PMF, let's see what is Ex, expectation of x. So for expectation x, I told you a simplified way. What is that? Just multiply x values with the corresponding PMF of x values. So 1 by 2 into 1 and 4 into 1 by 2. So their addition gives you 5 by 2. 1 by 2 plus 4 by 2. That gives 5 by 2. Similarly, you can calculate yourself. EY is 0 and EXY is also 0. Please do these calculations yourself. EX is 5 by 2, EY is 0, EXY is 0. Now what is covariance? Covariance is EXY minus EX into EY. You can clearly see it is 0. So for this joint PMF, we have found that covariance is 0. Now let's see whether XY are independent. For independence, let's check the first pair. What is the value of joint PMF at 1, minus 2? Means F1 minus 2. The value is 0. And what is the marginal density at 1? Fx at 1 is 1 by 2. And marginal density at minus 2, marginal density of y at minus 2 is 1 by 4. You can see that product of these two is not equal to the joint density. So this shows that xy are not independent, right? So this example shows that covariance may be 0, but the variables are not independent. It means converse of that result is not true. So now the question is then what covariance tells you? Of course, covariance doesn't tell the strength of, or you can say association between x and y, the type of association between x and y. By the way, in this problem, what is the relation between x, y? Can you guess? What is the relation between x, y? Is it y equal to x square or x equal to y square? It is x equal to y square, because if you square these values, you are getting these x values. So we are able to see the relation between x, y. But covariance is not telling anything about it, okay? But covariance has a feature to tell the relationship between x and y. What is that? It tells actually about the linear relationship between x and y via a coefficient called Pearsons coefficient of correlation. So I'm going to define Pearsons coefficient of correlation. Pearsons coefficient of correlation tells us the linear relationship between x and y. Let's see how. Pearsons coefficient of correlation. It is defined as rho xy equal to covariance xy divided by sigma x into sigma y. The Pearsons coefficient of correlation is defined as rho xy equal to covariance xy divided by sigma x into sigma y, where sigma x is positive square root of the variance of x, sigma y is the positive square root of the variance of y. That you know. Also we denote it by sigma xy. Covariance xy is denoted by sigma xy. So rho xy can be written as sigma xy divided by sigma x into sigma y. So this is the definition of Pearsons coefficient of correlation. Now let's see how it tells the linear relationship between x and y. It can be proved that, listen, it can be proved that rho xy lies in the range -1 to 1. This is important to remember. Rho xy lies in the range -1 to 1. Okay. Secondly, mod of rho xy is 1 if and only if y is equal to a plus bx, where b is non-zero. Y is equal to a plus bx, where b is non-zero. So this is how it tells the linear relationship between x and y. Okay? So when this Pearsons coefficient of correlation is 1 or minus 1, we will have a linear relationship between x and y. Okay? So what does it mean? If rho xy is 0, then we can certainly say that there is no linear relationship between x and y. Okay, see these plots where you will understand the meaning of this coefficient of correlation. Suppose x and y are lying on a line, then what will you get? Rho xy is equal to 1. Here you can see there is a positive correlation. As x increases, y also increases. If this is the situation, this is the situation of rho xy equal to 1. This is the situation of rho xy equal to minus 1. The x and y points could be like this also. In that case, rho xy is 0. The points may be like this also, scattered around a line. In that case, rho xy is very, very close to 1. In this case also, points may be scattered around a line. That means rho xy is close to minus 1. So this is the meaning of this Pearsons coefficient of correlation. Okay? If rho xy is equal to 1, we say that there is a perfect positive correlation between x and y. If it is minus 1, we say there is a perfect negative correlation. If this kind of situation, there is no correlation. But if correlation is 0, we cannot say that there is no relation between x and y. Not this point. Just before this, we have done one example where the covariance is 0. Covariance 0 means rho xy is 0. But x and y were related. What was the relation there? X square, y square, x equal to y square. In the previous example that we have done. Okay? So, correlation 0 means there is no linear relationship. But it doesn't mean that there is no relationship between the two variables. This coefficient of correlation only talks about the linear relationship between x and y. Okay? So, hope you understand what I am trying to explain. Alright, 2 more points, then this lecture would be over. Covariance matrix of x and y. Just you should know this. Covariance matrix of x and y is sigma x square, sigma xy, sigma yx, sigma y square. You know this is covariance xx, this is covariance xy, covariance yx, and covariance yy. Because these two are always equal, so it is a symmetric matrix. This matrix is called covariance matrix of x and y. Similarly, there is another matrix called correlation matrix. It is given by 1 rho xy, rho yx, 1. Why is it 1? This is correlation matrix. Correlation of X with itself. You recall this formula. Correlation coefficient, how you define it? You define it covariance XY over sigma X sigma Y. So if Y is equal to X, then you have sigma X square in the numerator and denominator also sigma X square, so you get 1. Likewise here you will get 1. Alright, so this matrix is called correlation matrix. So it is useful to remember these two. Okay, so with these points this lecture is over. Next time when we will meet, we will do a random sample. Okay, thank you.